This is an introduction to partially observable Markov decision processes, or POMDPs. I'm going to give you a quick refresher on Markov decision processes, motivate the POMDP framework with a healthcare problem, give you a formal definition of a POMDP, and use the pomdp solve software to solve a small two-state problem. I'll show you how to write the pomdp solve input file for the program, solve it, and interpret the output of pomdp solve to find an optimal policy. So what is a POMDP? I'm going to start with a quick refresher of an MDP, and then we'll generalize to a POMDP. A Markov decision process is a discrete time sequential decision-making problem with uncertainty. At any given time, the decision-making process is in a state little s, and from a specified set of states, capital S. We take an action A from a set of possible actions, capital A, and then we're going to move to a new state S prime. And this transition is random and happens according to some transition probabilities which are known. And these are conditional on the current state and the action. After this, we're going to get a reward that can be a function of the state we came from, the action taken, and the state transitioned to. Finally, we're going to repeat this process either an infinite or finite number of times, depending on the problem. So I'll give you an example of an MDP, and then we'll talk about why an MDP might not be an appropriate model for this problem. And then we're going to generalize to a POMDP. So this example comes from the 2011 Informs tutorial paper by Alagosh, Optimizing Cancer Screening Using Partially Observable Markov Decision Processes. The goal here is to decide when to do a mammogram for breast cancer with the goal of maximizing the quality of life for a patient which may need to undergo treatment for cancer. We have a finite horizon. The screening can begin at age 40, and we choose every 6 months from then on up to a certain age whether to have a mammogram or not. The state is the state of the cancer, starting with ranging from no cancer NC. We can have K different states of cancer, different levels of cancer progression or something, or post-cancer, and then finally death. So the action is at each stage is either do nothing or do a mammogram. So obviously an MDP doesn't really make sense for this. The state tells us whether a patient has cancer. A mammogram tests for cancer, so there's no reason to do a mammogram. In a POMDP, we add another layer of uncertainty. We don't actually know the state, but we can have some partial information about it. So let's generalize to a POMDP. First, we don't actually know for certain the state of the cancer, but we're going to maintain some probability called B of S that the cancer is in one of the states, and this belief will be based on what we can actually observe. If the action is do nothing, a self-breast exam can give a positive or negative diagnosis. Of course, the positive or negative diagnosis is not 100% accurate, and we can define probabilities of whether it's incorrect or correct. A mammogram can also give positive or negative diagnosis, and as you'd expect, it's also not 100% accurate, but it's more accurate than the self-exam. So what we've done is generalize an MDP. We still have states. We know the possible states, but we don't know which one we're in. Instead, we maintain a probability distribution over the states, which is the current belief of what state we're in. The action still constitutes the transition, but it's not visible to the decision maker. Instead, what we get is an observation, which we use to update our beliefs. In this case, positive or negative test results. So I'll give you a formal definition of an MDP. The formal definition requires 6 pieces of information: the set of states, the set of actions, the observations, the conditional state transition probabilities, the probability of states transitioning, even though not visible to us, the conditional probabilities of having an observation based on the actions that we take, and the reward function. So the process here is slightly different from an MDP. We take an action, the state transitions, same as an MDP. Now we're going to have an observation. According to omega, we're going to update our belief probabilities, and then we're going to collect a reward. It's a function of S. Since we don't know S, we're going to need to average that reward over possible states based on our current beliefs. Next, I'll talk a little bit about solving MDPs. I'm not going to go into all the details. Essentially, I'm going to give you enough information so that you can interpret the output of POMDP solve, which is a program that implements exact and approximate algorithms for POMDPs. So we can think of a POMDP as an observable Markov decision process with a continuous state, our beliefs. The state is the current probability that we're in each of the unobserved core states based on the observations that we've seen. So if we have a finite number of unobservable states, it's a probability mass function. The actions are the same as the original POMDP. The transitions are going to be updates using Bayes' rule of the belief probabilities updated each time an observation is seen. You can look at the equations for those on the Wikipedia page for POMDPs. So far, we have described a POMDP as a continuous state MDP, but we can't do the usual value or policy iteration because we have a continuous state. We can't do a lookup table. It turns out we don't have to. A POMDP is a special type of continuous state MDP. It's got a couple properties. Sondic and Smallwood showed first that if you have a finite horizon, the value function is piecewise linear and convex. This means that all we need to store is the line segments that make up the piecewise linear and convex function. If it's infinite horizon, it's still convex, and we can approximate it arbitrarily with a piecewise linear function. So it's going to be the maximum of a set of planes in either case. And what we're going to work with is this set of planes. Each plane called alpha is going to have some value v sub alpha of s for each state s, being the value of the value function given current state s. So if we knew the state, the value function would just be the maximum over alpha of v sub alpha of s. Instead, we're going to write it in terms of the belief probabilities. So remember, our state here is the belief probability, so we're going to maximize over all the planes that we have, and we're going to average the value of each state for the maximum given our current beliefs. And we're going to use these planes, or as they're usually called, alpha vectors, when we interpret the output of the solver. So I'll just show you graphically. Suppose we have two states, core states, unobservable states, 0 and 1. So then the planes are lines. So here we have some lines. Since it's a line, each needs to be represented by 2 points that are on the line. For convenience, we're going to define the 2 points by the values at 0 and at 1, our two states. On the 0 and 1 vertical axes, we see v sub 1 of 0 and v sub 2 of 0, v sub 2 of 1, v sub 1 of 1, which tell us the value at each of the states of these lines. So the red line is the upper envelope, which corresponds to the value of the optimal policy at each belief state. And at each line break, the optimal action to take is going to change. So what does this horizontal axis mean? This horizontal axis is all the possible beliefs that we can be in. So if our current belief here is that the probability of 0 is, this is something like 3/4, then we just look up here, and there's the value of it. So one thing that you might notice is that one of the lines is never part of this upper envelope. We don't actually need it. We only need 3 of them to represent the value function, and we should throw it out. So algorithms do a lot of work to throw these out. It's not too complicated, but I won't go into the details of how that's done. Okay, so let's show a simple 2-state POMDP. It's called the tiger problem. This problem, as far as I know, first time described as a POMDP is in the 1994 paper by Cassandra Littman and Kaelbling. Cassandra is who wrote the POMDP solve software. So here's the setup. You're playing a game show. There are 2 doors, left and right. Behind one door is a tiger. Behind another door is a prize. You don't know which is which, and you have to guess. And the game show goes on forever, unlike most real game shows. So we have 3 options. Open the left door, open the right door, or listen for the tiger. If the tiger's on the left, you hear the tiger on the left with some probability, 0.85 in this case, and you hear the tiger on the right with probability 0.15, and vice versa. So if the tiger is on the left, you're more likely to hear it on the left. and get some information about where it is. And same if it's on the right. So we can listen as many times as we want before opening a door, but we're going to pay a penalty. After we open a door, we're going to get a reward for choosing the door with the prize, and we're going to get a penalty for choosing the door with the tiger. After you open the door, the game is repeated. The tiger is randomly placed behind one of the two doors, and it goes on forever. So for technical reasons, we're going to need a discount rate. So the first thing we're going to do in the software is start with the line discount : 0.75. Anything less than 1 is going to work. So as I described the formal definition of the problem, I'll show you how to specify it in the pomdp solve software. This is the first line here, discount 0.75, and those descriptions are in that console font there. So we're going to go through the formal definition of the tiger problem, and I'll show you the software representation. So first we need to describe the state. Tiger's either on the left or on the right, and we'll represent the states. We'll call them tiger left or tiger right, and in the software we'll have this line, states : tiger left space tiger right. We can use whatever we want for the names, so it's convenient to pick descriptive names. So next we have our actions. We can open the left door, we can open the right door, or we can listen. And the actions, again, listen, open left, open right, and in the software, similar to how I've written it here, listen, open left, and open right. And I'll show you at the end the entire representation of the input at once. So our observations. So if we listen, we either hear the tiger on the left or we hear the tiger on the right. If we open the door, we're going to actually see where the tiger is. So you might think you want 4 observations, here left, here right, see left, see right, but really we just need 2, and we just need to either make them have some probability that's less than 1 or probability 1 if we actually open the door. So the line here, observations, tiger left, tiger right. So we need our transition probabilities. So we're going to need a transition probability T of S prime given SA for each pair of states that we can transition between, and each action A. So we're going to represent this with a 2x2 matrix for each action that we can choose. So if we open the left door, we reveal where the tiger is, and it gets randomly replaced in either left or right. So no matter where the tiger starts, it's randomly in either one. Same if we open right. If we listen, the state's not going to change. Even though our beliefs change, the tiger itself is not moving. So it's just going to be the identity matrix. So in the software we can write it like this. So we're going to have a T transition, listen, 1 for each of these observations. First is the identity matrix, and then those 2 matrices there, 0.5s all the way across. Since this is such a common transition matrix, we can actually instead use a shorthand here, identity and uniform. So we need the observation probabilities. Omega, like we said before, if we listen, we either hear the tiger coming from the left or the right, and we have an 85% chance of hearing the tiger behind the door it actually is. If we just open the door, we'll observe the tiger is in either door with a 50% probability. In the software, we're going to write this the same way as the transition probabilities. So for listen, 0.85, 0.15, and open left and open right are uniform. Last thing that we need to specify is the reward function. We haven't specified what the rewards are. It's really arbitrary here, but we'll say that there's a penalty of -100 for opening the tiger door, a reward of +10 for opening the door with the prize, and a cost of -1 for every time we listen. So in this case, the reward function is only a function of the current state S and the action A, regardless of where we transition to. In the pomdp language, you can describe the reward as a function of the action, the current state, the observation, and the next state. So instead of describing the function explicitly for all of them, which would be really redundant here, you can use in the software the shorthand asterisk to indicate any the way it's done in the table. So let's just look at the first line. You take the action of listening. No matter what state you're in, you are going to have a penalty of -1. So in the software, we're going to have 3 asterisks for everything except for the action. And similarly, for the other actions, opening left or opening right, depending on what state you're in, you're going to get some reward or some penalty for doing that. So once more, I'll show you on one page the POMDP solve representation of the tiger problem. So this completely defines the problem. With this, you can solve it and find out what the optimal way to make money and avoid the tiger is. So if you want to run POMDP solve, you need to download the source code for it from pomdpTutorial, compile it, and run it on the command line. It's a software that implements a variety of solvers for POMDPs. So you're going to run it with some options being the algorithm you're going to use in the input file and parameters for that algorithm if you need them. If you have a small problem, you can just use -POMDP, all one word, as your algorithm, and that will do a good job for a small problem. You should try that first. It worked on the tiger problem in less than 10 seconds, maybe less than 5. So after you run the code, you're going to get 2 output files. One is a .alpha file, and the other is a .pg file. So here are the PG and alpha files for the tiger problem. So the alpha file, like the alpha planes that we talked about earlier, encodes the value function. Each pair of lines lists an integer and a list of real numbers. The ith list of real numbers are the coefficients of alpha I, and the integer is an action corresponding to alpha I. So what does that mean, an action corresponding to it? So let's quickly just go back here. So let's say that you're right here, that your belief is about 80–90%, that state 0 is the true state, and then we're going to look at the maximum here is plane number 1, and remember that at each breakpoint our action is going to change. So here, anywhere within these belief states here, you're going to have some action corresponding to this line, and that's the integer in the alpha file. So there are exactly enough lines or planes described in the alpha file to encode the value function. There's no redundancies, unlike the picture I showed you before. So the PG file, PG stands for policy graph, tells you what actions to take depending on what observations you make, and together the PG and the alpha file can help you come up with or show you the optimal policy for the problem, or an optimal policy for the problem. So what you're going to want to do if you want to build the optimal policy is you're going to start with some belief, and then you're going to find the plane that is sitting, as in the picture, above that belief state, and you can do that by looking at the coefficients here. It's not so straightforward. If you use the POMDP solve parser at tarektaha.com, it's a MATLAB code where you can load up these 2 output files, and you can give it a belief state, and it'll tell you which plane is above the belief state and which action to take. So let's say we have done that, and we find that the maximum for our current belief state is the third one here. So then we're going to go to our PG file, the third one, so we're going to go to line 3. This first column is just an index of which alpha plane you should be looking at, or you came from, I guess. Then the second column is just repeating the action corresponding to that plane. And then there's going to be an integer for each observation that you can see. So here the observations, remember, are either tiger left or tiger right. So so we're going to take the action 0, which in this case is to listen, and then we're going to find out what an observation is according to the observation probabilities, and it's either going to be left or right, and then we're going to look at the columns corresponding to which of either of those two, left or right. So let's say it's right here, the second one. Then that's telling us to look at the first line here in the PG file, and then we can get our next observation, or take our next action, sorry, which is going to be to listen, and then we're going to get an observation, and either left or right is going to tell us which line to go to in the PG file. So we're going to repeat this process as you get more observations to tell you what to do as the problem progresses. So here is a graphical representation of what you should do. I didn't make this myself. This is from the 1994 paper that describes the tiger problem as a POMDP. So we're going to always start with a 50-50 belief vector because we have no idea where the tiger is. It's either left or right. So we're going to start here, and with a 50-50 probability, the optimal action is always to listen. And then we're either, of course, going to hear it on the left or hear it on the right. If no matter what happens, we're going to listen again. So let's say we hear it on the left, and then we're going to move to this listen node here, and then we're going to listen again. And if we hear it on the left, then we have a really good idea that the tiger is on the left, so we want to open the right. And then that's going to replace the tiger randomly, and we repeat and start over. So to summarize, what you're going to do is you're going to keep listening until you hear the same side twice, and then you're going to open the opposite door. This policy graph was made by doing this process here of looking at the PG output file, and it came from solving the problem using POMDP solve. So that's it for what I'm going to show you. There's a lot more to POMDPs. Solution methods and models using POMDPs are active areas of research in the operations research community, in artificial intelligence, in robotics. There's even some work in mathematical biology, mathematical ecology. So if you want to learn more about POMDPs, I suggest you start with pomdp.org, look at Anthony Cassandra's tutorials, and he's got a list of problems that people have solved. There's been a lot more since that's been written. I would also look at the Wikipedia page on POMDPs, and from there, your next bet is really to look at research papers on them. Thanks for listening and watching.